Hey, welcome back to today's video. Today we're going to start with a new topic, and that is an introduction into game theory. This is mainly meant as an application of what we've learned so far about vectors and matrices to see what we can do with these tools already. So I'm going to give you a short glimpse on some of the methods that are used in game theory to model real-life situations. And we'll start with a special setting that is called Bimatrix games. So today's section is Bimatrix games. Before I give you the definition and also explain where the name Bimatrix games comes from, let me first start with a small example to illustrate how these can be applied in practice. This example is a setting known as Prisoner's Dilemma. And it's one of the classic examples in game theory, and one of the games that we'll analyze in this chapter here. So the setting is the following. Imagine you're one of two suspects in a crime that have been caught by the police. Now you and your partner in crime are interrogated by the police separately, so there's no way that you can communicate. And each of you has two possible options. You can either choose to deny everything, or you can choose to confess. And of course, if you confess, you will confess that both you and your partner are guilty of the crime, and you'll try to put most of the blame on your partner. Now, the outcome of that little game here is dependent on what both of you do. So, of course, your partner does have the same options. He might also choose to put all the blame on you. And depending on what he does, you will be sentenced to some time in jail, and the number of years that you're going to serve will differ on the actions both of you decide to take. So let's take a few notes on that setting. As I said, the setup is we have two suspects in a crime. And let's say these are arrested by police and then interrogated separately. Each has two options. The first one is you can confess that both did the crime. Or you can deny any involvement. Now, the outcome of that game depends on the action of both criminals involved. Now, basically, there's three possibilities. The first is both could confess. Now, if both confess, they will both be sentenced to serve some time in jail, and the sentence will be 3 years. That's not the maximum possible sentence, but because they confess, they will get a little fewer years, so they will be sentenced to 3 years each. If both confess, they will be sentenced to 3 years in prison for each. The other option, of course, is they could both deny. And let's say the police does have some proof that they might be involved with the crime, but they cannot really prove they did all of that. So again, they will be sentenced if they both deny, but they will only be sentenced to serve 1 year. And finally, the third option is one of the prisoners could choose to confess, while the other will deny. Now that happens, the one who confesses will try to put all the blame on the one who denies, and the police will be able to use him or her as a witness against his partner in crime. And for that role as a witness, the one who confesses will walk. So he won't have to serve any more time in prison. While the one who denied his involvement in the crime will be heavily punished with a maximum possible sentence, and that is 7 years. So if one confesses, and the other denies, then the former will be freed, while the latter will serve 7 years in prison. Now, of course, the question here is, what is the optimal strategy? There is no way that you can communicate, so they will each have to make up their minds separately. And of course, we will assume, we will make a couple of assumptions. We will assume they cannot communicate. We will assume they have all the information, so they know which combination of actions leads to which sentences for both players. They also know the set of available actions, so there's nothing else they could do apart from denying or confessing. And they also know that the other knows the same thing. So this information is available to both. And the information is complete, not only in the sense that it involves all strategies, but also that the outcome captures everything that is of importance to this decision. For example, if one chooses to confess and the other chooses to deny, then with the sentences of 0 or 7 years respectively, that's all the consequence these actions will have. The one who confessed and acted as a witness against his partner will not have to fear retaliation. So this, of course, might be a bold assumption, but that will enable us to actually analyze what happens in this game, in this setup, and what the optimal strategy for each player is. So this is a simplification of a real-life problem, of course. As a theory, a model is always a simplification, but it will still allow us some insight into the dynamics of the interactions happening here. Now, as I said, the main question is, what is the rational strategy here? The optimal strategy. For the criminals. Now, I already said we have made a couple of assumptions, so let's jot those down first, and then we'll see how we can model that situation in a formal way. So one important assumption is that of complete information here. That means all aspects of the game are known to all partners, and there is no cooperation. There's no information that might still be retrieved. These aspects, those include possible actions. Those include payoffs. So the number of years spent in jail in this example, we would say that's a negative payoff probably, and so on, are known to all parties. And they know this. So it's not just that they have all the information, they also know this is all the information there is. Second assumption, there is no cooperation and no communication. So the two partners would have to agree on a strategy beforehand. That might be before they even know the setup of the game. They will not be able to communicate once they have all this information here. So in particular, each party chooses a strategy, an action to be taken independently. And finally, probably the most important assumption here is perfect rationality. So what that means is all parties involved behave perfectly rational. They will analyze what consequences their action will have. For example, they will assume if I choose that strategy, then what strategy might my opponent choose, the other player? Well, he might use that strategy and the outcome will then be this. And is this optimal for me? Just in terms of the outcome. So the only important aspect is the outcome, the payoff. Of course, each player would like to have a maximal payoff, but that's the only aspect here. So there is no feelings involved, and there's no retaliation involved, no revenge, or things like that. The players act completely rational. So all parties behave perfectly rational, and their only goal is maximizing their individual payoff. So towards their sole objective of maximizing their individual payoff. Okay, so these are the assumptions that we generally make in classical game theory. Of course, there are branches of game theory where some of these assumptions will not be necessary, replaced by more elaborate, more complex models. But in this quick glimpse at game theory, we'll stick to this classic setup. Now, let's have a look at the definition. So we will now define a formal framework that will allow us to come up with a model for the problem, the setup that we've just seen, the prisoner's dilemma. And then we'll be able to analyze this setup to see which strategies are the best possible strategies for both players. So the framework that I want to introduce here is known as Bimatrix games, or in the more elaborate wording, two-player finite strategic games. Because it's shorter, I usually refer to those as Bimatrix games. What does that mean? That's the first part of this definition. A so-called two-player finite strategic game or Bimatrix game is specified by, well, we need two numbers, m and n, those are natural numbers. And we need two matrices, that's where the name Bimatrix comes from. Most matrices will be called a R and a C, and they are both in R to the m by n. Now we refer to these m and n sets, so the sets 1 to m and 1 to n, as the actions of the players. So imagine one player has m different actions and the other has n different actions. So these numbers m and n, they specify the actions, the number of actions each of the players has. For example, in our prisoner's dilemma, the actions were confess or deny. So each player has two actions, m and n would be 2. So these are the actions or the action sets, and it's easy if we give those players names, and we refer to those players as the row player and the column player. They're called row player and column player because the actions of the row player will correspond to the rows of those matrices A, R, and AC. And the actions of the column player will refer to the columns of the matrices A, R, and AC. So the matrices have m rows for the m actions of the row player and n columns for the n different actions of the column player. So these sets are called the actions of the row or the column player. Respectively. And these matrices, those will be called the payoff matrices. Now the idea of those is if the row player selects a certain action, certain strategy that corresponds to one row, and the column player selects a strategy that corresponds to one column, then at the intersection of those two, there is an entry in those matrices. And that entry specifies the payoff that the row player or the column player will get if both choose these actions here. So the matrices AR and AC are called payoff matrices. For the row or the column player. And their entries at position I and J are the payoffs for the row player and for the column player if row selects strategy I and column selects strategy J. So their entries at position IJ with I in 1 to M, J in 1 to N, are the payoffs, the row or column player receives if row selects action I and column selects action J. And this specifies the setup of the game. Now there's two more things that I'd like to define. The first one is what is called a strategy or a strategy set. Basically, the strategy for one of the players is to select one of the possible actions. That's the basic idea. Now, sometimes it might be helpful to not commit to an action right away, but instead have some randomness involved in the game. So for example, if the column player would be able to exactly predict what the row player is going to do, then of course you can choose a strategy that will adapt to this behavior in an optimal way. For some games, that might not be a problem. For example, for Prisoner's Dilemma, it will turn out this is not a problem. For some games, it is. Think of something like rock, paper, scissors. You all know rock, paper, scissors. And actually, we'll analyze that game in a few more videos. But what happens here is, if you knew that your opponent was always going to use rock, then of course you would always use paper, or at least you would never use scissors. So it might be preferable to not be predictable in this game. And that means the only rational action here is to randomize. So you should not always use the same action, but you should put some random probability distribution on your action set. For example, you could just throw a dice, and then if 1 or 2 comes up, you select rock. If 3 or 4 comes up, you select paper, and if 5 or 6 comes up, you select scissors, all with equal probability of 1 over 3. That might be one possible action if you play that game, especially if you play it several times in a row. And that is actually true for a lot of games. And to capture that in the definition, what we do is we'll say a strategy might not consist of selecting a certain row or a certain column, but it could also consist of defining a probability distribution. So assigning to each row or each column a probability of selecting those. And then of course, we would not have a concrete actual payoff anymore, but we'd have something like an expected payoff. So if the game is played several times, then the payoff, the mean payoff, should be somewhere in the vicinity of that expected payoff. So that's the idea of these randomized strategies, or as they are also called, mixed strategies. Now let's define what that is formally. Formally, that is really easy, actually. So for a Bimatrix game, given by, I'm just using the matrices AR, AC, the two numbers will be encoded in the dimensions of the matrices from now on. So I'll just mention those are m by n matrices, and that defines the numbers m and n. And for such a game, we have two sets, and those are the sets SR and SC. Those are called the strategy sets for row and column. Those sets will contain all possible strategies, and to make the representation more concise, we are going to use vector notation for those. For the row player, we're usually going to use the letter Y to denote a strategy. And a strategy is a vector where each component of that other vector is between 0 and 1. And for the row player, that vector has n components. So for each row, imagine something like a probability assigned to that row. And of course, if you always play the same strategy, then one row will have probability 1, or 100%, and all the others will have probability 0. That means you're only playing one strategy. Okay, so that's this vector. And of course, if we want these entries to reflect a probability, then they will have to sum up to 100%. So with the sum of these entries of the yi is 1. So that's what defines a strategy for the row player. And of course, it's similar for the column player. We usually use the letter X for column strategies. Column has n different pure strategies, pure actions. So a strategy is a vector in 0, 1 to the power of n. And again, we want the entries to sum up to 1. So these sets are called row or column strategy sets. And each element, each vector in these sets is called a row or a column strategy. And finally, we will call a strategy a pure strategy if it consists only of 0 or 1 entries. So that means there's one entry and all the other entries have to be 0 then, meaning the player selects one action and only one action, no probability distribution, just one action. That's a pure strategy. And all the others are sometimes referred to as mixed strategies to emphasize they don't have to be pure, but they can be. So a mixed strategy can be pure as well. Pure is a special case of a mixed strategy. That's the wording here. Okay, so we say a strategy is called pure strategy if all of its entries are either 0 or 1, no fractions, and the strategy is sometimes referred to as a mixed strategy. To emphasize that it does not have to be a pure strategy. But remember, it can be. So mixed includes the case of pure. And finally, if we're talking about mixed strategies, then we also have to define what the payoff is. And in this case, we use the expected payoff. So for a pair of strategies, X in SC, Y in SR of a bimatrix game given by a R, a C, both in R to the m by n, the so-called expected payoff, and we sometimes leave out the expected, but we mean exactly that, even if we don't mention it explicitly. So the expected payoff for row is, well, what is that? The expected payoff for row is, of course, given by the payoff matrix, AR. Now, the column player plays X, the row player plays Y. So in pure strategies, we'd get the entry at position I, where I is the position of the one entry in Y, and J, where J is the position of the one entry in X. In mixed strategies, we just have to weigh each possible outcome with its probability. And to do that, we'll use the expression AR times X. So that basically weighs each column with the factor xj. So the first column will be weighed with x1, the second with x2, and so on. And this is summed up for each row. And then we do the same for the rows. To do that, we use the operation y transposed times in front of the matrix. So what this is a linear combination of the columns and then a linear combination of the rows with weights given in the vectors x and y. And of course, it's similar for the column player. So the expected payoff for column is very similar, basically the same expression. The only difference is, of course, we need to use the column payoff matrix. So there's an AC here, and here's an AR. Okay, so in particular, if I'm using pure strategies, for pure strategies, those would then be unit vectors. So let's say I have the ith unit vector for the row player and a jth unit vector for the column player. Then the payoffs are, well, the first is UI transposed times AR times UJ. And that would weigh the jth column with a 1 and all the others with 0, so they vanish. That means A times UJ is exactly the jth column of A. And then UI transposed times that vector will select exactly the ith entry of that column. And all the others will have a weight of 0, so they would vanish. It means what we get here is the entry of that matrix in position ij. So we denote that as a small AR for the matrix capital AR and the entry in position ij. That's what I mean by this here. And for the column player, of course, we get UI transpose AC times UJ, and that is AC AI. So we get the ijth entry of the matrix AC. Okay, that completes that definition. It was a rather long definition, but you see the application of that is not very difficult. So as an example, let's have a look at prisoner's dilemma. Let's try to model that as a bimatrix game. Now, for prisoner's dilemma, both of those players have two strategies. So the number of rows and the number of columns of all matrices is 2. So they could either confess or they could deny, and I'll just use confess as the first strategy, deny as the second, and I'll say these are strategies C and D. I'll write those beside the matrix to make things a little clearer. And the matrices are then, well, what's the payoff of the row player? So we need two rows, two columns, and those correspond to confess, deny here, and confess, deny here. So remember, if both confess, then they both are sentenced to a jail time of 3 years. So let's say the payoff is the jail time in years, and of course we want to make that negative, because the players usually want to maximize their payoff. So a negative number, a high negative number is bad. So let's say the payoff then is -3. The row player gets 3 years in jail. Let's do the same thing for the column player as well. She also has confess, deny here, and in the case of both confess, she also gets 3 years in jail. So there's also this -3 entry here. Now in case both deny, both get 1 year in jail. So both deny means we're here and here. Here and here. So this is the entry we want. And 1 year, that means the entry here is -1. No surprises so far. Now let's have a look at the case where the row player confesses and the column player denies. So this entry here. The row player confesses and is then used as a witness against the column player who denies. So that means the witness walks free. So there's a payoff of 0 years in jail here. On the other hand, for the same strategy combination here, for the column player, that combination would result in 7 years in jail. So the payoff here is -7. And finally, this situation, the row player denies, the column player confesses. That's the reverse situation. In that case, the row player gets 7 years in jail, so there's a -7 here. And in this matrix here, the column player walks, so there's a 0. Okay, so these are the payoff matrices for prisoner's dilemma. And now just as an example of possible strategies, so the pure strategy 1-0, for example, for the row player means, now what does that mean? That means the row player selects the first row with a probability of 100%. So that corresponds to confess. While 0-1, selecting the second row, that corresponds to deny. And of course, the same strategies can be used for the column player. An example of a mixed strategy, for example, that would be something like, let's say, 1/2 and 1/2. That would mean the player confesses with a probability of 50% and denies with a probability of 50%. So basically that's a setup where each player throws a coin, and if it shows heads, then he'll confess, and if it shows tails, then he won't. So mixed strategy. That means player confesses with a probability of 1/2, so that's 50%, and denies with probability 1/2. So that's a 50-50 decision. And of course, that could be a valid strategy. Well, if I don't want the other player to know what I'm doing, to be able to predict what I'm doing, then I could employ such a strategy where I myself might not know what I'm doing. I'm going to toss a coin, and that will give me my decision. Okay, so that's a possibility for a mixed strategy. And finally, let's have a look at possible payoffs. So just as an example, say Rao chooses to confess, and Column denies. What is the payoff then? And for Rao, the payoff is then determined as when the Rao player confesses, so the strategy is 1-0, transposed AR times, and the column player denies, so the column strategy is 0-1. So that will be 1-0 transposed. The matrix AR is right here, -3-0, -7-1, -1, sorry. Times 0-1, and what will we get? I'll start with multiplying the matrix here and this vector, and that will give me 0 times -3 plus 1 times 0. That obviously is 0. And for the second column, I'll get, for the second row, sorry, I'll get -7 times 0 plus -1 times 1. That's a -1. And multiplying those two, I get 1 times 0 plus 0 times -1. So the expected payoff is 0. In this strategy combination, the Rao player walks freely. And of course, that is exactly what we defined in the rules of the game. That should not be a surprise. For column, the payoff would be the same, but with a C instead of AR. So we get 1-0 transposed. Now AC is -3, -7, and 0, -1. Times 0-1. So here we get 0-1 transposed times -7, -1. So that is -7. And again, not a big surprise, the column player is sentenced to 7 years in jail in this setting here. Okay, so that concludes our introduction into bimatrix games. We'll further analyze Prisoner's Dilemma, and we'll also introduce some other examples for games in the following sections and see what we can say about the optimal strategies for the players here, and if there is a valid choice for an optimal strategy for games like this one. I'll see you then.